The goal of this video is to take a graph of a function f of x and be able to identify or even draw a graph of its derivative f prime. Before we start, I have something start at the top as just a reminder. As we go through, we're going to list some defining features and key observations, and those things are going to be predicated on this reminder that I have listed above. So remember, when we're given a graph of f, the graph of f prime is going to output the instantaneous rate of change for f of x. So all the outputs in our graph for f prime that we're ultimately going to draw here, each one represents the instantaneous rate of change at that respective x value in f of x. So if our goal is to draw or model f prime, we want to pick out some features of f of x that will give us some information about instantaneous rates of change. And where people typically start, and it's a good idea to start in these places, are wherever we have maxes and mins on our f of x. And the reason why is because at maxes and mins, we have horizontal tangents. Okay, so if I look at f of x, I can pinpoint two minimums and a maximum. That maximum should actually be on the origin in this case, so let's be a little more precise. Oh. Okay, now, so that's our first defining feature, key observation. That's where we want to start. Where f of x has a max or min there is a horizontal tangent. Now, why do we care about horizontal tangents? Horizontal tangents have instantaneous rates of change of 0, right? Their slopes are equal to 0, which would imply that our graph of f prime of x is going to equal 0 where I have horizontal tangents, which means that we're going to be able to identify x-intercepts. Wherever we have horizontal tangents, we're going to have x-intercepts on our f prime graph. So something that people like to do, which I actually find helpful myself, is if we add in these dotted lines to keep things in line nicely, and we can break up basically our graph into these sections that we can analyze individually. So if I carry down these dotted lines through my max mins, which again I encourage you to do if you have to draw a derivative graph. Actually, let's redo that one. I can now see exactly where I would want to pinpoint my zeros or my x-intercepts. So we're going to put those right there, there, and there. Okay? So I've located where the x-intercepts of f prime should be based on where the max mins of f of x are. And again, f prime of x outputs instantaneous rate of change. We know at max mins we have horizontal tangents, and horizontal tangents have slope of 0, which is why we have x-intercepts there. Now, the next defining feature we want to look at is where is f of x increasing and decreasing? And then we'll look at where is it, when it's increasing, decreasing, at what rate is it increasing or decreasing? So, if f of x is increasing, that would imply that the rate of change is positive, which means if f prime represents the rate of change, the graph should be greater than 0, and visually that means it will be above the x-axis. Okay, so outputs will increase on a function if the rate of change is positive. So if I know that f of x is increasing, I know f prime is positive, and therefore in the section of the graph that we've now divided up with our pink dotted lines, where we have sections that are increasing, I expect to see f prime to be above the x-axis in that region. If f of x is decreasing, then we know that f prime of x is less than 0, because the rate of change would be negative, And visually, that would be below the x-axis. So in the regions where I see f of x decreasing, I expect to see the graph of f prime to be below the x-axis. Now we need to look at the rates of change of the rate of change in order to get the most accurate picture. So we're going to take this part a little slower because this can be a little tricky. Let's break down again. If f of x is increasing, and we're going to look at two scenarios. Increasing at an increasing rate, at a decreasing rate. So the reason we have to do this is because once we've identified that f of x is increasing or decreasing, we know where it is in relation to the x-axis, but we don't know is it increasing or decreasing while I'm above or below, and that's what this second piece is necessary for. So if f of x is increasing, we already know that based on this fact here, we already know that f prime of x is going to be positive. So the question now is, is f prime of x, when it's above the x-axis, is it increasing or decreasing? Well, that's what's revealed in these second two parts. Okay? If it's increasing at an increasing rate, that means that f prime of x is positive and increasing. Because remember, the rate reveals, it tells you it's increasing rate, so it's telling you what the derivative is doing. The rate, which is the derivative, is increasing. Okay? And we'll look visually how to identify that in a second. But if f of x is increasing at a decreasing rate, we know f prime of x is positive because f of x is increasing, and then the derivative itself is decreasing because the rate is decreasing. So there's a name for these things. It's called its concavity. And what we're looking for when something's increasing at an increasing rate, it's going to look something like this in that region. If something's decreasing at a decreasing rate, I'll even just get rid of the arrow just so you can see something like that. So it's increasing at a decreasing rate, it's going up, and it's going to look something like that. Okay? Next, what if f of x is decreasing at these different rates? So if f of x is decreasing, we already know that the derivative is going to be negative at increasing rate, at decreasing rate. Okay, so we already know that f prime, once we've identified the section of the graph for f of x is decreasing, we already know this part's negative. Again, the question then becomes, if I'm able to identify that I'm in the negative region of the graph below the x-axis, is my graph supposed to go up or is it supposed to go down, right? So is it supposed to be increasing or decreasing in that specific section? So if it's decreasing at an increasing rate, again, the word rate is in reference to the rate of change. So it's telling you the rate of change is increasing. So we know that the derivative should be increasing and decreasing. So visually, what does that look like? If we're decreasing at an increasing rate, it's going to look something like this. And if we're decreasing at a decreasing rate, it will look something like that in those regions. Okay. Those pieces that I've drawn for the visual, that's looking at its concavity. So we're going to just define concave up is going to be when the rate at which a function is increasing is increasing. Actually, let's define that better. Let's say concave up, much more simply put, is when the rate of change is increasing. And again, as a visual, you're going to see something like this. Okay, think of concave up as if you poured water into this thing, it would hold the water. Okay, that's concave up. Concave down is when the rate of change is decreasing. Because as we can see in our graphs, the rate of change at various points isn't going to stay constant all the time, and the concavity reveals that information. So we could have something like this, that, or maybe we have a full section. But concave down, you can think of it when you pour water on something that's concave down, it just runs off the side. It doesn't hold the water. So now we have all the information we need to graph. So let's go back to our original graph. We have our graph of f of x. We're going to attempt to draw f prime. So we've already identified where the zeros are. In my leftmost region, this is decreasing. Now at what rate? Well, this looks like it's decreasing at an increasing rate. That looks like it's concave up to me. So it's decreasing at increasing rate, which means because it's decreasing, I know f prime of x is going to be below 0, and at an increasing rate, f prime of x will be increasing below 0. So it's going to be something like this. Now, we're going to jump all the way over to the far right. This is increasing at an increasing rate. So as we can see, that looks like it's concave up. Okay, so increasing at an increasing rate, the increasing implies f prime of x is above, and the increasing rate implies that f prime is increasing itself. So it looks something like this. Now, what's going on in the middle? Well, there's two other points that we need to be able to identify, and I'm going to plot them in green. There's a point where the concavity switches over. Okay, so like when I'm looking in this second region here, we can see that it's concave up initially, and then it kind of switches over at a point right there where it becomes concave down. And same thing in this region. We have a point where it switches concavity, and that is called an inflection point. So let's take note of that. So we can say point of inflection it's where f of x changes concavity. Where you have points of inflection, you will have a max or a min on f prime. So f prime will have a max slash min at points of inflection. So let's go back to f prime. We can see at first along this piece that's concave up, so it's increasing at an increasing rate. So f prime is going to be above 0, and it will be increasing. And then we reach the point of inflection, and this graph is increasing, but now at a decreasing rate. So f prime will still be above 0 because f of x is increasing, but because it's going at a decreasing rate, f prime starts to decrease. Okay, so now you can see where that max comes from. So right when the change in concavity occurs, we have a max for f prime. Then following the blue graph again, now it's decreasing at a decreasing rate because it's concave down in that section. So decreasing would imply f prime is below 0. At a decreasing rate would imply that it's below 0 but decreasing. Then it switches over concavity at the point of inflection, so now it's decreasing at an increasing rate. Decreasing below 0 at an increasing rate, it's increasing. Okay? So a couple key features. You can identify the zeros for f prime by finding out where maxes and mins are for f of x, where your horizontal tangents are. You can identify where max mins are on f prime if you look to see where points of inflection are on f of x. And again, the point of inflection is where it switches over concavity. Now, let's say we have f prime, we want to jump to f double prime. Same procedure. Let's figure out where our horizontal tangents are. So f double prime is the derivative of f prime. So it works the same way. We have a max, we have a min, so that tells me where my zeros are. So let's carry down, we'll do a different color here. Let's do it in so we're going to carry down these lines. It's pretty light. I don't know if you can see that. But either way, we have them lined up so that our zeros are there and there. Okay. Now, I actually am going to darken that because I want to be able to see the sections of the graphs. And then we add in yeah. So now, I'm going to erase the pink so we can get a better look at f prime. So there are our sections. We have 3 sections. We've identified where the zeros for f double prime should be. Now let's look in the leftmost region. F prime of x. This is increasing, and that's concave down, so it's at decreasing rate, which means that f double prime should be positive because f prime is increasing, and f double prime itself should be decreasing since it's concave down. So it's going to be something like that. Okay? Now, for the middle section, we can see that f prime is decreasing the whole time. So I expect f double prime to be below the x-axis. Now, at what rate is it decreasing? Well, from there to there, it's decreasing at a decreasing rate. It's concave down there. So because it's decreasing and concave down, the graph of f double prime is going to be decreasing and below the x-axis. And we can see that it switches concavity again right in the middle, which again, we have a point of inflection where the change in concavity occurs on f prime. So I expect to have, in this case, it looks like it's going to be a min for f double prime, and I will because it's decreasing, but now it's decreasing at an increasing rate in the second section. So below the x-axis, and it's increasing since the rate of change is increasing. Okay, now, the last section, from here on, f prime is increasing at an increasing rate. So if it's increasing, then f double prime will be greater than 0. And if it's concave up, that means that f double prime will be increasing itself. So it looks something like that. okay? And it'll be much smoother, more of a parabola shape. So now, that's kind of a lot, so let's jump over to Desmos to see a really nice visual of what's actually happening. So here on Desmos, I have a picture of our initial f of x graph, and I've plotted a point a f of a. What I'm going to do is I'm going to add in a tangent line so you can see kind of how the rates of change are evolving as we move along the function curve. So first off, let's write our tangent line. So in class, we've already discussed, we're going to do y minus the y coordinate, which in this case is f of a, equals, the slope will be found by doing the derivative at a, so f prime of a, and then x minus a. And you can see a tangent line was just added in. I'm going to change the color to white, and now that point A is going to run between -3 and 3. And look how the tangent line slope, again, represents our instantaneous rate of change at a point. So you can see that in the section, this leftmost section, the graph of f of x is decreasing. I'll even turn this off for a second. You can see the leftmost section, the graph is decreasing. And you can see that when I put the tangent line up, the tangent line slope is negative, which is what we said. Now, if I run through this, you can see that the tangent line slope is remaining negative up until the point where it reaches our first min. And when we get there, we can even check the value of f prime of a. And you can see that the output here is 0. So we have a horizontal tangent there. Now, let's also observe the fact that when this graph was decreasing, you can see that it's concave up, okay, in that leftmost section. Now, when it's concave up, we expect the rate of change to be increasing. So let's pay attention to f prime of a, which gives us the rate of change at a. So if I take this back, as I move down the function curve, can you see how the values of f prime of a, which are over here, are increasing in value as I move along a curve that's concave up? So while the function's decreasing, this is decreasing at an increasing rate. We reach our horizontal tangent. Now it's increasing at an increasing rate. So the f prime value is going up, right? Now in the second piece, the second region that we have, we said there was a point of inflection. So let's see if we can see where that occurs, or roughly where that it actually even exists. So as I bring my tangent line, now you can see that that portion of the graph is increasing. And we said it's increasing, and then at an increasing rate where it was concave up, and then there's a point where it switches over to being concave down. So you can see my tangent line as I run it through. The tangent line, I know the slopes are they're increasing because the tangent line is getting steeper. And then there's a point where the tangent line starts to flatten out. It's no longer getting steeper, right? That point where that changes over is where the point of inflection is. So it's getting steeper, so I know the slopes are increasing, and you can look at the values, it's increasing, and then all of a sudden, if you look at the values of f prime of a over on the left, you see how now they're decreasing again. So the rate at which this is changing, it's increasing, and then it switches over to decreasing until I reach that horizontal tangent again, where we expect it to be at 0, okay? So we can see a point of inflections occurring there. And then one more time, this section's decreasing, and again, we can see a section's decreasing when the slopes of the tangent are negative, and you can see why that's what we chose as our way to identify if a region's decreasing, right? So this whole region where I said it's decreasing, you can see that the tangents always has a negative slope, okay? Now the question is, how is the rate of change changing? It's concave down, so the value of f prime, if you look over to the left again, it's decreasing for a while, and then there's a point of inflection where it changes over. Now it's going to start increasing again. And there it goes. So see how it's increasing in value again until it reaches the point where we have a horizontal where it's 0, and then it's concave up for the rest of the way. So our analysis of rates of change, how they are changing themselves, where things are increasing and decreasing, makes sense. So what I'm now going to do is I'm going to get rid of this tangent line, and we'll get rid of the point. We're going to plot f prime. Okay, so what does f prime look like? Exactly as what we expected. We can see that where we have a max and a min on f prime is where we have the points of inflection on f. You can see that where we have zeros on f prime, we had max or mins on f of x, exactly as we predicted. We can also see that where f of x is decreasing, so in this region here, for example, we can see that the graph of f prime is below 0, exactly as we predicted. Okay, so you can use this computer technology to verify that you did something correctly. And now I'm going to remove f of x. So now we're just looking at f prime. Let's look to see what f double prime should look like and see if that fits what we also predicted. And it does. We get that parabola shape. And again, let's just look at the point of inflection on f prime, where it changes concavity, reveals a min slash max. In this case, it's a min of our derivative of that graph. We also see that where we had max and min on f prime, we had zeros on f double prime, exactly as we predicted. We see where f prime is increasing, f double prime is above 0, where f prime is decreasing in this middle section, we see that f double prime is below 0. So all the defining properties that we need have been identified to successfully graph a derivative of a function.